And so the talk for today is about the moduli space of two convex embedded spheres, which is joint work with Buzano and Hershkovits. So to get started, let's start with the one-dimensional case, which is the space of embedded circles in the plane. Somewhat more formally, that's the quotient space of all embeddings of S1 into R2 mod the diffeomorphisms of S1. So meaning we care how the circles look geometrically, but we don't care about the parametrization. Okay, so that's a infinite dimensional space which comes equipped with the smooth topology. So then you can ask, well, what actually is the topology of the space? And this was proved by Stephen Smale in '59. So what Smale proved is that this space of embedded circles in the plane is actually contractible. So it's homotopy equivalent to a point. Maybe the first remark is that there are many different equivalent ways of stating Smale theorem. So saying that M1 is contractible is equivalent to a bunch of other things. So, right. So maybe for to get started, we have embeddings of the two disk into R2. And embeddings of S1 to R2, and they're related just by the restriction map. So that's the restriction map. And saying M1 is contractible is equivalent to the assertion that this restriction map is a homotopy equivalence. So why is this? Let's try to understand this together. So first of all, there are embeddings of the two disk. There isn't that much. So there, just take the differential at a point. Then you see that is homotopy equivalent to GL2R. And then here you also have a map which is just take the differential at a point. Then you get a 1/2 matrix, and then you write a unit normal vector next to it. So you see this restriction map is always surjective, but then you have to figure out, well, when is it injective? So, right, so GL2R, of course, deformation retracts to O2. So then the last bit we have to understand is what is diff S1. So that's quite simple. So if you want to say what is a diffeomorphism of the circle, well, then you first specify the image of one point. So that's a rotation, and then what is remaining is a diffeomorphism of the interval to itself that fixes the boundary. But those maps, they are just strictly monotonic functions, so you can deform them to the identity. So that's contractible. Okay, so meaning diff S1 is O2, which is the homotopy the same as GL2R. So then you have all those pieces together to see that this restriction map is a homotopy equivalence if and only if this quotient space here is contractible. Good. So what else can one observe? So then you can look at this map again. So that's in fact a vibration. So the fibers here are just diffeomorphisms of the disk that fix the boundary, keep the identity at the boundary. And so that's a homotopy equivalence if and only if the fibers are contractible. So if and only if the diffeomorphisms of the two disk relative to its boundary are contractible. Okay, so let me emphasize again, everything in this talk is smooth topology. So a continuous world is a different world. There you just do the Alexander trick, which is a nice trick, but which isn't that useful in the smooth setting. Good. And then this game you can in fact play for spheres of any dimension. So similarly, diffeomorphisms of S2 decompose as O3 times diffeomorphisms of the two disk relative to its boundary. Okay, meaning if that is trivial, that means that the space of all diffeomorphisms to the two-sphere deformation retracts to O3. Okay, and let me also quickly mention some special cases of Smale's theorem. So if you look at pi 0, well, then maybe look here, then you see, well, this restriction map, okay, at pi 0, so that means that every embedding of the circle actually comes from the embedding of the disk. So that's the Jordan Schoenflies theorem, the smooth version of it. And if you look at pi 1, and if you trace to those, so this topology exercise for computing pi 1 of M1 amounts to computing pi 0 of diff S2, so that says that diff plus S2, so the orientation preserving diffeomorphisms is the space is path-connected. And that was proved a year earlier by Mankres. Good. Okay, so that's the topology exercise. So then for the sake of motivation, let me give a geometric analytic proof of Smale's theorem. Okay, so we start with some closed embedded curve in the plane. In fact, we start with all closed embedded curves in the plane. Then what we want to do, we want to deform them to some canonical model. And the way you should deform curves if you're a geometric analyst is, of course, by curve shortening flow. So you evolve the curve in time, and the normal velocity at each point is given by the curvature vector. So that's the normal component of the velocity, which is the only geometrically meaningful component. So tangential deformation just amounts to a change of parametrization. So if you do this, then you get a one-parameter family of curves, gamma t. starting at the given initial curve. Then you can, well, figure out how does this evolve in time, and then it's a really beautiful theorem due to Matt Grayson that this actually always converges to a round point. So if you evolve it, it can look very complicated at the beginning, but then it evolves in time, and then it looks rounder and rounder, and then it shrinks and becomes extinct in finite time. And before it becomes extinct, if you zoom in, then you see exactly the round circle. So that's classical and beautiful theorem due to Grayson. So the curve shortening flow exists until t. Maybe let me do this one-line computation. So you can also explicitly compute this time capital T. So here you just look at the enclosed area. Let's call this A of t. So then you can compute, okay, what is the rate of change of the area? Well, you move by curve shortening flow, so the curvature vector is the curvature without vector times the normal vector. Then you look how does the area change, so you just have to integrate the curvature along the curve. So that's minus the curvature integrated along the curve, but since it's an embedded curve, that's minus 2 pi. So you see the initial area divided by 2 pi, that's the maximal possible time how long it could possibly exist. And Grayson's theorem, it says it indeed exists until this maximal time, and it becomes extinct in a round point. Let me call the point x depending on the initial curve, and what I mean here is that, well, after rescaling to unit size, you converge to a round circle. Okay, so now let's see. So now we want to understand why does Grayson's theorem prove Smale's theorem. Of course, to prove Smale's theorem, you shouldn't just flow one curve, but you should flow all curves at the same time. And then well, let me just write down the map. So the map goes from the space of embedded circles times the unit time interval to M1, and it maps gamma comma t to. So essentially, it's curve shortening flow. But then I have to do some rescaling that for each guy the isotopy happens in the unit time interval. So let me write down this factor here, a gamma divided by 2 pi times t. And then I also have to shift the center point that everyone moves to the same point at the end. So let me write minus x gamma plus 1 minus t x gamma. And then I have to rescale the whole thing, let's say, to unit size. So put this square root 1 minus t. Okay, so if you define the map I this way, then, well, then you see, first of all, that I of gamma comma 0, well, then that's just 1, the initial thing. Minus plus x, so I of gamma comma 0 is just the curve gamma we start with. Then the limit t to 1 of I of gamma t. well, by Grayson's theorem, that's this rescaled thing here. So that's the round unit circle. And then, since the curve shortening flow depends continuously on the initial data, this map I is continuous. Okay. And this proves Smale's theorem. Okay, good. Any questions about circles in the plane? Yeah. Okay, if not, then let's move on to M2, which is the space of embedded two spheres in R3. In other words, the quotient space of embeddings of S2 into R3 mod the diffeomorphisms of S2. Okay, so then it was conjectured by Smale when he wrote this paper that M2 is also contractible. There's a theorem from Haslhofer from 20 years later stating that M2 is contractible. And the remark is we can do the same topology exercise that we did before, just one dimension higher, to see again that M2 contractible is equivalent to a bunch of other things, in particular equivalent to saying that Diff S3 is homotopy equivalent to O4. Okay, and to do this topology exercise, you have to know what Diff S2 is, so you have to use Smale's theorem. So meaning always, if you know one dimension, then you can do this reformulation in the next dimension. Good. Okay, and let me again point out the special cases. So that M2 is connected, that's Alexander's strong form of the Schoenflies theorem. And the M2 is simply connected, that is Cerf's theorem that this plus S3 is path-connected. Okay, and that's a highly non-trivial theorem, so that in particular implies that if you know what gamma 4 is, that implies that gamma 4 vanishes, and that was used a lot in topology. Good. Okay, so that's the case n equals 2. So now let's move on to general dimension n. So kind of still write down what is Mn. So it's the n spheres in Rn plus 1. So that's embeddings of Sn into Rn plus 1 mod diff Sn. Okay, but writing it down is about the only thing you can do about the space. So naively you might say, okay, well, M1 is contractible and M2 is contractible. We would just keeps on going like this, but let me point out that's completely wrong. So the naive guess that Mn is contractible for all n is completely false. So why is this? Let me quickly explain this. If Mn were contractible for all n, well then, arguing as above, we could see that the diffeomorphisms of the disk relative to the boundary are contractible. However, it is known that this has non-vanishing homotopic groups for every n bigger or equal to 4. And even more strikingly, for every n bigger or equal to 6, there are actually infinitely many non-vanishing homotopic groups. Pardon?
Is this for every n?
For every n bigger or equal to 6, yeah. Okay, and n equals 3 is a big question mark, of course, so that's related to the Schoenflies conjecture and the smooth Poincare conjecture and so on. Okay, but anyhow, in general, the upshot is, well, in general dimension, the topology of the space of embedded spheres is extremely complicated. And so then of course, what people in geometric analysis want to understand is what is the interaction between curvature and topology. So we've seen that the topology can be extremely complicated, but then one can ask, well, all those, is the reason for this complicated topology is the spheres that don't look like a sphere at all. So it's all this exotic topology caused by spheres that are geometrically not at all like a sphere. Again, to make this question more precise, one needs a suitable curvature condition. And so the curvature condition for our case is two-convexity. So a closed hypersurface is two-convex if the sum of the smallest two principal curvatures is positive. So lambda 1 up to lambda n are the principal curvatures, the eigenvalues of the second fundamental form ordered by size. Okay, and that's a useful curvature condition. Well, one reason is that there's a classification result due to Heusken and Sinestrari. Which tells you, well, if you have a closed hypersurface that is two-convex, then it's diffeomorphic to either the sphere or the torus Fn minus 1 times S1 or a connected sum of those guys. So by the way, there's a similar story in Riemannian geometry. So there are all those exotic spheres and so on. But if you impose some curvature conditions, for example, quarter-pinched curvature, quarter-pinched sectional curvature, then it's only the standard sphere. Good. Anyway, so what we consider now is the space of two convex spheres. Okay, so clearly two convex is a geometric condition, so it's preserved under change of parametrization, so it makes sense to consider this subspace of two convex embedded spheres. And then the question is, what is the topology of this subspace? And so the conjecture is that M and two convex is contractible in any dimension, meaning that all the complicated topology comes from spheres that are very far away from around embedding geometrically, meaning not two convex. And the main theorem for today. So this is joint work with Buzano and Hershkovits. Is the pi zero part of this conjecture. Okay, let's see. Good. Okay, so the proof uses geometric analysis, namely mean curvature flow with surgery. Good. So the very basic idea of flow with surgery is, well, you do mean curvature flow for a bit, and then you hit some singularity which looks like the neck pinch, and then you cut along the neck and glue in caps and continue the flow of the pieces. Maybe actually you do two surgeries, but then this piece in the middle here is a piece of known geometry and topology, so you throw it away. Good. Okay, so most of the time it's just smooth mean curvature flow, but then there are finitely many times where there can be either this cut and paste procedure or discarding pieces of known topology and geometry, or both. Right. So by now there are like several versions of mean curvature flow with surgery. So this was first done by Huygens and Sinestrari in the case n bigger or equal to 3. Then by myself and Kleiner in all dimensions with a simpler proof, and independently also by Brendle and Huygens. And the version I use here is the one from my work with Kleiner. Well, we use this version because, first of all, I've been involved with writing the paper, so I kind of know what's going on. But more importantly, it comes together with the canonical neighborhood theorem, And that's quite important for the topological application. So let me say very roughly what is a flow with surgery. So it comes with some scales, 3 curvature scales. So one scale is what we call the H thick, which is much less than the neck curvature, which is much less than the trigger curvature. And all those curvature scales are very large. So what is a flow with surgery? So at all but finitely many times it's just smooth mean curvature flow. And then, the curvature is always bounded by this trigger value. So that's the upper bound for the whole procedure, and surgery and or discarding exactly happens when the maximum of the mean curvature hits this trigger value. Okay, then the surgery is done on a minimal collection of delta necks with curvature H neck that separate the thick part and the thin part. So here in this picture, that's the thick part and that's the thin part. Minimal collection of disjoint delta necks of curvature H neck that separate the thin part, meaning where H is maximal, from the thick part where H is less than or equal than this H thick. Again, that delta neck is just something that after rescaling it to unit size is delta close on a ball of radius 1 over delta and C1 over delta to the standard round cylinder. And delta is a very small parameter. Then there was one more condition. So then we discard exactly those components which has H bigger than H thick everywhere. And for those high curvature regions, we have the canonical neighborhood theorem, so we know exactly how those discarded components look like. Okay, so then for today's topological application, the main claim to prove the theorem, which was on this board, is that if you look at the flow with surgery, then all connected components are isotopic via two convex embeddings to what we call a marble tree. Okay, so let me say what is a marble tree. So marble tree is something very, very explicit. So that's you take some round spheres and some controlled curves between them, and then you glue it along those tubular neighborhoods. So this comes with some explicit model. Okay, so something like this is a marble tree, well, and then it's not a lemma. We prove that any marble tree can be deformed via two convex embeddings to a round sphere. So you see how this goes. So you do induction on the number of marbles. So you pick a leaf, shrink the leaf, contract the tentacle, and that's about it. Good. Oh, and this also comes with some parameters. So the parameters is so there's this string radius, this radius of those tubular neighborhoods where we do the gluing, and then there's this marble radius, the radius of those spheres here, and then there's all those other scales which come from the flow with surgery. And the point is just, well, to pick the string radius and the marble radius much smaller than any other scale in the problem. So then those different scales almost don't interact. So much smaller than H trigger inverse. So that's H trigger. That's a huge number. But if you pick those scales even much smaller, and then if you do the gluing, then this trigger scale looks like almost flat. Okay, so then let me explain how to prove the main claim. So the proof of the main claim is by backwards induction on the surgery times. So to get the induction started, we have to look at the extinction time, that the final flow, where the flow becomes extinct. But at the extinction time, all connected components are entirely covered by canonical neighborhoods. And therefore, by the canonical neighborhood theorem, just from this surgery paper with Kleiner, we know that they either look like almost round, or the second possibility is that they look like a long chain of necks that are capped off on both sides. And it can't be a round thin torus by our assumption on the topology of the initial surface. So we just have those two cases, and then in either case you can deform it by hand to a round sphere. Okay, so then the main point is the induction step. Again, you can, in the picture here, see what's going on. So by induction, if you continue flowing, then we have the isotropy for this piece and for this piece and for the discarded piece. And then the task is to glue together those isotopies to build one big isotropy of the whole whole thing. So the induction step amounts to gluing isotopies. Meaning we have those different components, and then we select curves connecting them, connecting the caps, and then we have to glue along those curves, and we have to do this in a continuous way for one parameter families. Let me just state the gluing theorem. So here, let's say XAB is the space of AB controlled configurations of domains and curves. Okay, so that is something that looks like this. And then the idea is this describes the gluing configuration, so that's the input, and the output is this connected sum along those tubular neighborhoods of those curves. Here one can also have those loose ends where one has this capped off cube. Okay, so let me first say what is those control things. So for the curves, it means that the curvature is bounded by this parameter B inverse, and that the derivative of the curvature is bounded by b to the minus 2, and that the normal injectivity radius of those curves is at least, say, b over 10. And so that's the control parameters for the curves, and the control parameters for the domain. So that's a bunch of parameters. So that's alpha, beta, little c, and capital C. So little c is a lower bound for the mean curvature, and capital C is an upper bound for the second fundamental form and its derivative. And then we said it's too convex, but one can make this a bit more quantitative and put a little parameter beta in here. And also we said it's embedded, and there's also a quantitative version of embeddedness, which is called alpha non-collapsed. So embedded tells you that, well, you can put little interior and exterior spheres at every point, and alpha non-collapsed tells you that those spheres have radius at least this constant alpha divided by the mean curvature at that point. Good. Okay, so that's the input of AB controlled configurations, and the output of the gluing map, that's just two convex domains. And then the gluing theorem says there exists a smooth equivariant map gluing gluing at scale r from x, a, b to the two convex domains, which is defined for all string radii which are small enough such that it does what you see in the picture. So it doesn't add any topology, so the glued thing deformation retracts to the union of the domain and the curves. And then the gluing construction is local, so away from those little delta balls, it's just the initial domains or the R-tubular neighborhoods of the curves. And at those loose ends, it's those tubes capped off by a standard cap. To construct this gluing map, essentially what we had to do is understand two toy cases to understand how to glue a round sphere in the cylinder. Well, there you do some second-order Taylor approximation, and then you try to bend this before you hit the axis, and then you have to solve some differential inequality like t squared a double prime plus 4t a prime plus 2a less than 1 for a function a which goes from minus 1/2 to plus 1/4 in the interval from 0 to 1. And such a function indeed exists. And then you have to do the second thing is you have to understand how to glue a saddle surface and a cylinder. And for this, again, you have to so if you have a saddle surface like the graph of x squared minus 1/2 y squared, then you just want to deform this coefficient from minus 1/2 to plus 1. And then you see you need some other function, let's call it b, which satisfies t squared times b double prime plus t times b prime less than some small number, and it also goes from like 0 to 1 or something. But that's actually easier because that's a scale invariant condition. So you just move it up a little bit, and then you do it again at some smaller scale and keep on going until you reach the point 1 where you want to go. Okay, so I think I stop here.